I'd like to introduce myself first. I work on a lot of computers. The millions of containers hosted on hundreds to thousands of machines, all deploying our customers' websites. By our measures, we do about 1/1000th of the page views of the internet, which at the same time sounds like very little and very lot. So it keeps us busy. We are one of the largest kind of cloud users on the web in terms of instances and traffic. And we run USENIX.org, which we're very proud to have as one of our earliest enterprise customers. As for my background, kind of outside my company, I'm on the Drupal security team. I'm a core contributor. I'm a committer to systemd, and I'm on the Fedora server working group. So the idea of how the intersection of machines on the web deals with security on the web and high availability is something that I deal with every day. And one of the things that we've confronted over the last year are vulnerabilities kind of coming down the wire for libraries like OpenSSL, for programs like Bash, where we need to quickly analyze everything in our infrastructure that is dependent on that component. It could be a program directly that we run, like Nginx, or it could be just something that maybe Nginx loads. And so it gets pretty complicated, and even though we're very familiar with our own infrastructure from a kind of maintenance and development basis, it's still very hard to know the libraries that someone else has included into their applications, which we make abundant use of. So just kind of walking through different approaches to updates. Let's say another Poodle or Heartbleed comes down the wire today. How can people respond to that? Various ways I've seen. Of course, a lot of distros just kind of recommend install and reboot, but it's super disruptive on your infrastructure. Sometimes if you pack enough onto machines, they're going to be out for minutes, maybe even up to an hour at a time, bringing all the services back online that you had running. But it's one of those kinds of things where no one seems to know a great alternative solution to that. On distributions like Debian and Ubuntu, they try to build in this little bit of restart where, let's say you update Nginx. As soon as you update Nginx, it's going to try and restart the Nginx service on the box. But it's woefully incomplete for managing security issues because of the three that I mentioned, Heartbleed, and Shellshock, only actually 0 of those would have been dealt with automatically by having aptitude restart main daemons once you update them. Plus, it doesn't help you at all if you deploy multiple instances of Nginx or Apache or applications like that. You can try and think your way through the problem where you might be able to figure out that you're using OpenSSL with Nginx and using OpenSSL with Apache, and those are the things you therefore need to restart after updating it. But it's also really hard to know. We've found a surprising number of applications load OpenSSL and even make use of the SSL components in it. And we never would have guessed some of those things. So what I'm going to actually introduce is a method and a tool for analysis of running executables and libraries to figure out what's loaded, what's stale, and then to be able to figure out how to remediate that without resorting to rebooting an entire box. And this works for everything except for static linking and cases where you might have an application that might bundle its own libraries together with it in something like opt, but there's really no helping that. There's no way to tell that that's been updated except for them publishing an update. So assuming you're mostly using libraries and applications that are bundled with your distribution, this should work pretty well. But it's also hard to do by hand. So I created a tool that we use on our infrastructure. This is kind of an adapted open sourced version that allows doing this analysis extremely fast and then even doing some of the remediations extremely fast. So first, this is kind of a novel method of analysis that wasn't possible even a few years ago. The Linux kernel maintains maps of what files are loaded into what processes. It's through the procfs file system. And we're able to very easily map, going way back to, I think, Linux 2.0, map which processes have loaded stale things off of disk that have been, say, updated underneath them. But the actual method of being able to map that back to actionable things is really something that has come into maturity with cgroups and systemd. So how this works is we basically iterate through the procfs maps. We can find ones that, where there are things mapped to that actual process that have been deleted underneath it, which that's what happens when a package updates. The library gets swapped out underneath the running application, which are annotated that way, where they can still be mapped into memory. That's why applications don't generally crash when you update the libraries. But it does know that it's been switched out and keeps one copy in memory, and then it has the new copy on disk. And then what we can do is we can use cgroups to map those PIDs with stale maps back to systemd units. That one of the nice things that happens whenever you start a service in systemd, which is going to be the case for CentOS 7, RHEL 7, SUSE Linux, as well as the Ubuntu release that just came out, and then the next Ubuntu LTS. Every time you start a service, it starts in a C group, and then all of its children are in that C group. And the C group has the kernel maintain a mapping from process IDs to the name of that C group. And then what systemd does is it uses that to track what process IDs are part of what services on the system. And then we can restart the matching units and then kind of remediate remaining processes that don't seem to map back to any particular service. So the map data, I'm no longer widescreen, so I apologize if some of these are wrapping in ways they didn't before. But you can see that this is an example from OpenSSH running on a test server I created last night, where I installed the server, I updated packages, and then I took this snapshot. I haven't actually rebooted the box. I haven't done anything else. But you'll see here that these are marked as deleted. And that's because this library here has been swapped out underneath this particular application that's still running with the old version of it. And then what we can do is we can take that process ID, which was 1728 that we looked at the map of, and then it has things have a bunch of C group controllers, but one thing that will always be on boxes with systemd is there is a part of the tree in C groups that is just for tracking the association between processes and services. So as a human, I could have certainly looked at the command line of that and figured out, oh, that's SSHD. But this is actually an automated way to map it back to services so that you can have an automated response to the service being out of date. And then we can restart the service. I'm not showing the automated version of doing all this right now, just kind of the manual steps. So we can restart the service. It has a new PID down here now. And, or actually, this is still running the old one. But I must have misordered the examples in here. But you can do a restart in the service, and then when you do status on it, it's going to show that it just restarted. And then you can also kind of dive more deeply into some of this to figure out, is this update that has occurred underneath my service that I'm running actually a security update? One way to do that, of course, is to set your OS to only install security updates, and then you know that any update that's come down that has caused a daemon to be out of date is going to be a security update. But there are some tools for investigation. Like, we know that this is the path of the file that was out of date. And then and there are equivalent things on aptitude for all of these. And these slides will be online, so you don't need to kind of try to memorize any of this. But you can do rpmqf, and then that'll basically tell you what the actual package name is behind something. You can get the changelog out of a package and grep for CVEs to find out the last time that that had a kind of major reported vulnerability that was fixed by an update. So in this case, November 1st, 2013 was the last time on 3.15.2-3. we can see the last time we actually updated a package on the system, which the last time this got an update was the 14th of November 2014. And this service started on November 14th, but before the actual package update got installed. So it's pretty hard to guarantee here that it actually has the update. But you can also kind of look at the older history or know, you can look at logs to see whether when the actual security update came down the wire, because the update we're looking at right now is actually not a security update, clearly. I want to show the utility kind of in use, what it does. So it walks through almost all of these steps except for the kind of yum and RPM ones manually, or sorry, automatically. And then what it does is it traverses the maps of the system, and then it finds the deleted items. It takes those ones with deleted items, it considers those to be kind of actionable processes, and then what it does is it tries to find the remediation strategy for each of those things, where it will either try and map it back to a systemd service by using that technique I was showing with cgroups, or it will try and aggregate all the things based on the command line that was used for launching them, so that, let's say you have something that has 32 instances on the thing on your box with processes, like an Apache process pool. Well, Apache is probably not the best example. It would correspond to a service. But if you had a bunch of processes that are the same, it aggregates those, and then you get a kind of concise list of reasons of this service needs to be restarted because these things got swapped out, or this command line that is running a current set of processes is stale because of these things that are loaded by some instances of it. And so it's super easy to use. You just use pip to install PMR. It's called that because it's the process maps restarter, because it's basically investigating what things are mapping via the kernel and then deciding what to restart. You obviously have to install the updates to the system because it can't detect that something needs an update unless something has actually been swapped out underneath the running service. You can do a dry run with it, and this is kind of what the results look like in a very summarized form, where if you do verbose, you can see all the green ones that are basically things that it's validated that are completely fresh. But if you run it without verbose, you're only going to see things that it knows how to remediate and things it doesn't. So in this case, there are two examples of something it knows how to remediate. It found that libaudit is out of date for cron, one of the libraries that it's using, and it knows that it can restart that. The SSHD is loading a bunch of outdated libraries, including some that are kind of concerning if they're getting updates. Like libcrypto, I believe, is from OpenSSL, as well as several other kind of security critical libraries. And then there is a process down here, USR SBEN cron d-n, that it could not map back to a service, but it is running an outdated copy of libaudit. And that red means that even if I take off the dry run, it's not going to know what to do about that. It'll keep telling me that it's out of date, but it's hopeless to do it unless it gets extended in some way to know what to kill or what to do, because it likes mapping things back to services because it knows how to restart those. You can tweak the rules after a dry run. There is an INI file for it for units and command lines, and this is a great thing to tune for infrastructure, where what happens here is you can give it kind of whitelist, blacklist rules for different services and commands, so that if you, let's say, run a server where you ensure that you're deploying only your code to that server, there's no customer code on the system, you may only be concerned about certain services that are exposed to the web. And then you could create a whitelist for those to include them in this analysis as kind of security critical results. Or alternatively, you could do this where you match all services, and then certain services you know are very internal and unlikely to be actually attacked, like say cron D is very unlikely to have a remote exploit to it. Then again, bash, you'd think that for bash as well, but you can kind of blacklist that so that it doesn't show up in the reports. And then that way you can also control not just the dry run output, but the actual services and commands that it tries to remediate. And then you just apply the changes. You just run PMR's root, and it will show you the whole report that you got from the dry run again, as well as actually walking through restarting the services one by one with a little bit of delay between them. One nice thing with this being combined with systemd is, in terms of how to restart the services, is that it's dependency aware. So if it restarts a service that requires another service or another thing needs to go down in order to finish restarting this and bringing it back online, that's handled in the dependency layer that's specified in the service files themselves, rather than PMR having to understand the dependencies between these things. So it should do a coherent, kind of almost transactional approach to reloading and restarting these services. So I'll kind of demo it. Here I have my box. I brought it up last night, and the only thing I did is I started a Fedora 20 instance on the Rackspace cloud, and then ran yum upgrade on it. But I haven't actually done anything other than dry runs of PMR since. So what we can do is do a dry run here, and what we can see here is that syslog has a couple systemd libraries that have been updated. And we can see here that dbus, which is kind of an internal machine local service, also had the lib audit update. You're seeing actually a kind of very large amount of collected updates here, because this is from an image install to an update, whereas on a day-to-day basis, you would see a much shorter report. So we also see here that my user service which is kind of the service running my user session, needs to get bounced, as well as the kind of cron D example and SSHD examples that I showed before. And then we have all these other things down here that have outdated libraries but do not correspond to a service directly managed on the system that it could find through cgroups. And other than SSHD over here, and possibly our syslog, depending on how you have it set up, it looks like these are all machine local things. So they're lower kind of priority to be fixing if we control the machine local state. So I'm going to run this. Ooh, I didn't like that one. That is. One second. Yeah. Let me reinstall the PMR thing. Let's see if that takes care of it. Oh, I think it actually is just reporting failed inappropriately. I think it actually succeeded in restarting those things. I'll patch the, because it's not restarting the same ones again. And I can actually see, I should not have done the last minute patch for that. But if I do SSHD on here, you'll see that it actually restarted in the last minute. So it is actually restarting those successfully. I'm reading the output incorrectly for telling you. So now if we run the PMR dry run report, often what will happen is that these other things that it can't quite map back to services actually do correspond to services, in the sense that they might be managed outside the cgroups tree, but the service is interacting with them and reloading them. So the only thing we have left on here that is actually having any issue is the systemd journal, which is also a machine local service that's only getting interacted with by machine local processes and users. So that shows how it does that kind of analysis. And let's dive briefly into the code and kind of show how that works. There's my patch of doom. Better restart output. So what this does is it first, of course, kind of loads your configuration. It tries to pull the process list off the box. It has, even if you're doing a dry run, this has to run as root because you can only access the process map data if you are a root process. So it gets the process data, and that's all through this kind of running process mechanism here, and then it does the analysis in here. And then what it does is it iterates through all these processes with getting reasons. And getting reasons is basically find me a reason to blame a process for having something out of date. And it is walking through the maps. It is looking for things deleted, either from opt or USR. This could probably get expanded with more kind of custom rules in the configuration so that we could support the other directories that might be having files that are getting security critical updates. Like occasionally you can sneak those through etc with things like symlinks. But generally, process maps actually resolves any kind of symlinks or other things before you see it in the process map. So even if you're telling Apache that you should load this shared object as a plugin for like mod PHP, and that gets updated, even though it's loading it through the symlink in etc, it's actually going to be in the process map shown as from USR. So it has a very standardized output that has existed for the better part of 15 years. So it basically just parses and looks for that and looks for items that are deleted. And then what it does is it supports kind of two ways of taking this back to something actionable. Get the command line and get the unit. Get the command line just pulls the CMD line entry out of procfs. When that's empty, it's generally a kernel thread. So I'm just ignoring ones that are empty. Every time that I checked, they were related to some sort of kernel migration process or a related thing that can't just be restarted from user land. The get unit uses the process I was talking about before, where it looks in procfs for the C group, and then when it finds a C group that is owned by systemd, and I suggest you not name your C groups if you do custom ones systemd, because that would confuse this. What it does is it kind of splits out that path, and then the final part of the path of the unit, or of the C group, is the name of the service. And then what it'll do is, if it actually maps back to a real service, then what it's going to do is include it, return that as kind of the unit that it is. And in systemd language, a unit is kind of this abstract superclass that includes mount points, auto mounts, services, timers, really anything that is a kind of file on disk that you can configure. 99% of the time, these are going to be services. Maybe 1% of the time, they'll be mounts, because mounts actually have kind of a sub-process generally running in user land, especially if it's fuse-based. And then what it does is it's, after getting that data, it gets the units from any processes it can find it on. It gets the command lines from any processes it can find it on. And it's going to walk through all of those and then check whether it matches the strategy. And matching the strategy gets handled by checking, using that configuration file where if something is blacklisted, then it basically says, no, I don't care about that. If it matches one of your whitelist rules, then it will actually, it's a candidate for being included in the restart. And then if you haven't actually done any rule that matches it for or against, then it kind of falls back to the fallback of not including it. Because while you may want to include everything, from a security basis, it can be very disruptive to run this in your infrastructure and just give it kind of blanket ability to restart services. So I typically recommend kind of this iterative thing of like do dry runs on your boxes, collect the data, then you can kind of create things that are whitelisted. You can reverse that behavior by giving it a wildcard within the whitelist, and then the fallback will just be that everything matches. Once it matches the strategy, it will display the information. If you set it to be verbose, it will show it for everything. Including all the things that are green, which those are the things that have been restarted went green on the system because they now have completely up-to-date data underneath them. And then if it actually has a reason to restart that related thing, then it will append it to the list of services that are ready to restart that it will do if you actually are not dry running. And then if it's just a command line thing, it doesn't actually know how to remediate that. And this doesn't yet have the ability to put in custom rules for those things. But you could, of course, take the output of this, pump it into anything that you want, and make that decision. Or you could decide that there are too many red things on here and you just want to restart the box. And at least you can make an informed decision that that's really necessary. So with that, I'm actually going to open the floor for questions because I imagine that I may need a little bit of time for that. Because we do this for about 1 million containers on our infrastructure, and when Heartbleed hit, we had to restart about 100,000 processes across our stuff, but we didn't want to reboot those boxes. It would have taken our infrastructure down for hours. And if you do have questions, please use the microphone.
Hello. Oh, hey. Patrick Cable, MIT Lincoln. I was curious. I think OpenSL is a pretty ubiquitous kind of dependency. Do you have any insight into looking through your containers and finding other dependencies? And the other question was about how long did it take to rebuild all those containers?
Well, other things that we're seeing as dependencies that are kind of repeatedly used in the containers. Let's see. Often we see a lot of, say, Python libraries that are being pulled into processes, and then they may get an upstream update through pip or through a package manager. And then a lot of our services are written in Python, so we see that all the time. Often a Python library is just a wrapper of something in C.
Sure.
So what will happen is that I'll wrap that, we'll update a C library, and suddenly something in Python actually needs to be restarted.
So do you have a way of mapping those dependencies, or is it kind of going off of knowledge of the application at hand?
The great thing about this is it implicitly kind of recursively maps those dependencies, because if your application is loading, it's Python, it's loading something like PyOpenSSL. PyOpenSSL has to map OpenSSL.
Right.
And the kernel knows the fact that there might be 100 things on the system that are mapping OpenSSL, and it's only going to wire it into memory once. So it's not like it's duplicating all these things for every process, but it's still maintained as part of the process map for that Python application, because it needs to be, OpenSSL needs to be in the address space so that PyOpenSSL can call the C functions, so that Python can call the PyOpenSSL functions.
Great. Thanks.
Hey, so I'm pretty Debian biased, so that's where my head's coming from. But in dpackage, you have the ability to register your dependencies on libraries, and you have the ability to trigger actions on package update. So libc or OpenSSL is a really great example where if you've got your metadata registered, even if it's an application that you've rolled in-house that depends on OpenSSL, if your dependency tree is defined properly, why couldn't you just rely on that? Why do you resort to grepping through proc?
Well, it's incomplete for a few ways. So for example, on our boxes, we're running an nginx instance for every single container. And that kind of rule set will cause it to automatically restart the main nginx service that got installed with apt. or from dpackage. And that means that all of the other Nginx processes that are actually loading things that are currently insecure are not going to get caught by that. And then the other issue is that it's quite hard to actually map all those dependencies that way, where it's possible for, say, Nginx to say that it has a dependency on OpenSSL, but it's possible to create a package that installs, let's go to Apache now, a package that creates mod PHP, which then is loaded by configuration for Apache, but the Apache package has no idea that it actually has a dependence on something from mod PHP, and as far as mod PHP is concerned, it's just a library.
But that seems like it's more of a problem that you have multiple management systems with incompatible metadata, right? Like if you're per customer, per instance, Nginx installs, were registered as being dependent, then you could restart,
But
you see what I'm saying?
yes, I see. You could extend the system to allow registering additional things onto Debian's management of that. You still wouldn't be able to handle things like, for example, on PHP, you can do a dynamic load of an extension from PHP while you're running a PHP script. And so we can't actually, unless we kind of tried to hammer or chip away at different functions of the PHP language that our users use, they might use that, and then they would be loading a library that we certainly wouldn't have the metadata in dpackage about. Also, we use Fedora systems, so we don't actually have that. Like, we basically decided that we're not doing that in the package manager on the Fedora side, or the RPM side.
Coming at it from the other direction, what would be the benefit of, instead of having this as your own little Python script, actually trying to get it into systemd so that systemd itself knows that a library has changed and, oh, well, now I can just restart the things that depend on it?
So I talked to Leonard about this for including it possibly in systemd, and the kind of reasons why it's not in systemd is that one, on, say, the Debian side of things, there is a fundamentally different place that Debian wants to do that. They don't want it to be necessarily happening at this layer. Even though I think this is possibly a more comprehensive approach to the problem, it's not where Debian wants it. And if Debian doesn't want it there in systemd, then we really don't want to put it into systemd that's going to go out to all distros. The other case is that there are many exceptions that this can't solve, and we don't want to create overconfidence in this solution, where with those cases of static linking, like OpenSSL ships with a statically linked, it ships with binary data that you can use for statically linking OpenSSL into your application. And if you do that, then the memory mapping happens differently, and you may not actually have it show up on here. And then you may have the applications in places like opt or other places, or even things like packages like Google Chrome package a ton of libraries with the package and don't necessarily get updated on the base system when they need to get updated. So this is not a 100% approach. This, to us, based on the way that we use packages and we use libraries, is something like a 99% approach. And generally, we can decide that when on a security issue by security issue basis, whether this is appropriate or not. And for something like a system library, OpenSSL getting updated, this is an appropriate tool to use.
If nobody has any other questions, let's have a round of applause for our speaker.